Welcome everyone. We just heard an exciting, excellent colloquium by Aaron Parsons, and I find it personally exciting for two reasons. One is that many of us theorists at the ITC work on predictions for the 21 centimeter signal, and perhaps within a year there will be a detection. We so hope. We will keep our fingers crossed. And the second reason that I find it exciting is because it confirms a prejudice that I had, or a notion that I had, that work in small groups leads to breakthroughs more often because the group is more versatile, more flexible, allows free thinking in directions that were not prescribed ahead of time.
And no project management.
Yeah. And what?
And no project management.
No, there is always a project.
Oh, okay.
But the point is that if the management is flexible in its thinking and is willing to adjust to new ideas as time goes on, rather than have everything set in stone to start with, just because the group is big, there is more chance at getting at the truth this way. And in fact, there was a paper on AstroPH just a couple of weeks ago showing that there is a correlation between the rate of important breakthroughs and the size of the group. An inverse correlation, that was the less, and it certainly applies to theoretical projects, but now there is an excellent example also for an experimental project within astrophysics. There were previous examples like the MATIC project, which is more relatively collaboration. So today we have a number of visitors. We'll start with Joss Hawthorn, visiting us from Sydney, Australia, down under. And we're risking giving you the first lot, assuming that you stay within the time limit. Usually we use our representatives to show how it's done. They often go over time, so we try to do it.
I'll try not to.
And Joss will talk about chemical tagging in ultra-faint dwarf galaxies. After that, we'll hear again from Aaron Parsons from UC Berkeley, and he will talk about measuring the 21 centimeter monopole. So rather than doing the power spectrum of the sky, measuring just the spectrum of the sky, so to speak, with an interferometer. And after that, we'll hear from a newly appointed professor at Harvard, Matt Hersch, from the History of Science department at Harvard. And he studied NASA, and he will talk about the Geeks in space, NASA's scientists, astronauts in Project Apollo. And we'll conclude with Alicia Soderberg, our own, and she will talk about Type 1a supernovae progenitor systems, diagnostics from deep radio survey. Joss.
Thank you very much. What a wonderful crowd. I did not expect this. I've done more work. So anyway, I hope this is an interesting result for you, interesting way forward, an entirely different take on realization from this wonderful talk we heard just recently from Aaron about the HERA project. So this is chemical tagging in ultrafaint dwarfs. Chemical tagging is something I started developing back in 2000, 2002 with Ken Freeman, and we've been applying it to dwarf galaxies. This was the thesis work of David Webster. There's a picture of him here. He's putting in his first job application next week. He's a fabulous young theorist, and he has the distinction of being Australian junior chess champion, runs a marathon in a ridiculously fast time. He's a very, very talented individual, and would be a good fit with Harvard. So, that wasn't a plug. So here's one of the questions I want to raise in my very short talk before Avi hits me with 10,000 volts. Can we detect specific signatures of the first stellar generations today? This has been around for a while now. Recent reviews on the left-hand side, in annual reviews, the one by myself, and oops, what is all this about? Do I authenticate? Disconnect. Ah! Thank you. Oh my God. So the one I was on was with Volker and Torgny Carlson, who was a postdoc of mine in Reviews of Modern Physics, and we addressed this question: what kinds of signatures might you expect from the first stars, and the second and third generations, and so on? Right from the outset, I always wanted to concentrate on the lowest mass galaxies for a number of reasons. One is they would get going, hopefully, before reionization. They'd be also very affected by the reionization. And finally, how on earth does one get rid of that? Do you not have people from outside your system speaking here normally? Does it happen more than twice? And also...
if you come from the southern hemisphere.
Okay. There is a polarity problem with my machine. I noticed that earlier. So, and with me probably. So the effects of ionization is most clear, I think, on the lowest mass systems. And finally, we also think the lowest mass systems will give you the clearest chemical signatures, sort of inhomogeneities that you would expect, and hopefully use those to learn something interesting. The trouble is, where do you look for first star signatures or even second generation signatures? Do you look at the metal poor stars in the halo on the left? Do you look at faint dwarfs, ultra-faint dwarfs, or do you even look at globular clusters? There's no particular reason to think that the lowest metallicity are where the answers are. I mean, we know that globular clusters are ancient. The metallicity may just determine the cooling that was required to get to a given density. So it's not obvious where you should look. So more specifically on the signals of reionization, which is a very different take on Aaron's work, ultra-faint dwarfs have already been claimed now as being as preceding reionization and maybe even being influenced by reionization. There's a number of papers just in the last couple of years. I've got on the left-hand side. The diamond indicates theory, and the other ones are observational. Brown, I'll show Brown's results in a moment. But there are more and more ultra-faint dwarfs being observed. Of course, they're very, very low mass, very, very low, sort of 10 to the 5 sometimes, 10 to the 4. They may only have 10 or 15 stars that you can observe at all with an 8 meter, 10 meter, although the next generation telescopes will help. As a result, it's very difficult work in terms of measuring accurate abundances. But already the signatures are particularly interesting. So the papers I'm going to just mention briefly are the ones by Webster, myself this year, and at the bottom, the recent observational paper by Webster, Frabel, and myself on Segway 1. And there are new papers coming out by Frabel's group on reticulum and others. So here was the result published very recently by Tom Brown. And it's for 6 of the ultra-faints. Along the bottom you have a cosmic timescale, 14 down to 9 billion years. And vertically you have cumulative star formation history. And the point they make, say for example for Bootes 1 here, this is Hercules. The point they make is that if they use, at least in terms of their own isochrone modeling that they've done, they would claim that most of the star formation is already done by before ionization, by redshift of say 10 or 8. Slightly different result was published by Weiss et al. But when I asked this group why the results are somewhat discordant, Weiss et al. Has his star formation history over this line. They would argue that the ACS observations from HST are in fact better and give them more accurate star formation history. So the method that I wanted to introduce was the idea of chemical tagging in ultra-faint dwarfs. The first paper I wrote on this in the context of dwarf galaxies was 2010, AppJ. And then there was an application to sextants by Carlson. Then we talked about it in more detail in the Reviews of Modern Physics. And then there's this new result, which I'll show you from Segway 1. First of all, chemical tagging is just the idea that stars are born in sort of complex collapsing clouds. And one thing we were aware of, worked with Ken Freeman back in 2002 for our review, was that all open clusters, I mean all open clusters, are chemically homogeneous to a very high accuracy. Globular clusters are homogeneous in many lines, although some globular clusters show multiple branches and are not homogeneous. But one thing we work out in that paper is that we would anticipate that any star cluster up to 10 to the 5 would be homogeneous in all elements. And you could even show that with the density of a globular cluster, that you could even have something as massive as 10 to the 7 that would be entirely homogeneous. This work got some very nice support recently from Feng and Krumholtz, who revisited that paper with their modeling, and they showed how you get these complex fingers that probe into the center, which almost certainly guarantees homogeneity at a high enough density. Basically what you're doing there is causing enough mixing to occur before the first supernova goes off. So you want it all to happen within 3 million years, depending on the mass function of stars. So I made a prediction in that paper in 2010. This is for an 8 meter, this is for the GMT. This is R to FE versus FE upon H. And the point I was just making is that you get spread when you've got very few events. And as time goes by and you form more and more stars, this spread basically converges to some mean yield of metallicity yield for the population. And here for the GMT, the point I was making is that if you had the GMT, you can get 2 magnitudes fainter, and you could pick out even more star clusters. And that inhomogeneity at low metallicity, Fe upon H of -4, that would be washed out with the same number of events, but you see more stars. So I was somewhat surprised when the Japanese approached me on the back of that paper and said, well, you should look at sextants because we think we already see the effect. So here is barium to iron versus iron to hydrogen. And here are background stars for the halo. I think this is for the disk population. And you see a big spread in the 6 stars, the 6 giants they can detect below a metallicity of -2.5. And 4 of them look very bunched. And they look very bunched in 5-dimensional, 6-dimensional chemical space, as we show in the paper. It's very nice, actually. So if this is confirmed as a real star cluster, this is the most metal poor cluster that's been detected, or inferred, I should say. And this is magnesium to iron for the same sexton's dwarf. You can actually see a little bit of a hump in the iron to hydrogen distribution, which is also quite interesting. I suppose more spectacular is this new work, and there's more coming down the pipe from Anna Frabel. So if she comes to speak to you soon, you'll see the up-to-date results. This is for the, what is it? This is for Segway 1, and this is iron to hydrogen. And this only has 1,000 solar masses of stars. And somehow it got from a bunch at -3.5, a bunch at about -2.5, and a bunch up near -1.5. An amazing result. And in fact, this is all the giants above the detection limit. With GMT, you're down to about 21. So hopefully in about 7 years, you'd hope to be getting down to this level. Interestingly, strontium and barium are somewhat suppressed. And the timescale for the star formation inferred by the modeling is something like less than 50 million years. So I don't have time to dwell on details. These are the models that I published in 2015, this year. And we looked at a rather complex situation where you have dark matter halos of 10 to the 7, well below the minimum mass scale of 10 to the 8, because we're sort of before ionization. We have off-centered stars, we have fractal media, which we think is more realistic. And we're also resolving supernova shock fronts, and we have time-dependent ionization, because we look at the precursor ionization before the supernova goes bang. And we find enough of the gas survives, and we get enough elemental abundances to work with. And then if you plot those for different situations, so top left is just type 2s, middle these are 2 burst type 2s, 2 burst type 1a, type 2 and type 1a, and a 1 burst. Then you have other models with more complex. These are the 1 burst on the top. I'm so sorry, and these are the 2 bursts on the bottom. And here's Segway 1, Reticulum 2, which I think is the one being worked on now. They've got more abundances for this one, more stars. And this is all the UFDs combined in metallicity spread. So just to mention very briefly, there's an analysis in that paper about whether the clustering is significant. And this is from David's thesis. And he shows that sort of a 3-burst situation is what you would need to explain that result. I'm almost done. And he goes on to talk about what possible configurations might work in terms of whether you have to go 1, 2, 3. Is it most metal poor, then intermediate, then the most metal rich? Does it have to be in that order, or could it be in some other order? In fact, you can actually there's more than one order to get those, to form those within one ultra-faint dwarf. So it's not a unique time dependence yet. And let me just say finally, if you look at my paper in 2010, I actually have a comment at the bottom. The proposed experiment will be challenging for 8-meter telescopes. I wasn't even sure if we'd see it, but relatively straightforward for a multi-object spectrograph on a 25 to 40-meter telescope. I had the GMT in mind because Australians work directly with the GMT. So GMT and GCLEF working on together. And we don't even need a multi-fiber positioner. Andy St. Georgi recently said to me at Monterey that we could even think about plug plates. So we're looking at the idea of plug plates on the GMT to do this kind of work. And I know that you're involved in GMT, so this is work I think that will be directly relevant to a number of you. Thank you. What about, yes? That's right. Yeah, so we haven't actually sort of dialed up the full possibility of tables yet. We're basically at the point of just plausibility that you really are seeing the signature of clusters. that low mass and high mass stars are formed together at high redshift. So we're basically in the plausibility domain. At some point, if we have enough of these ultrafaints and enough chemical signatures, we would like to differentiate these sorts of models. We haven't got there yet. Oh, I hope so. On a very different topic, so do come along.
Am I on? Yes, I am. All right, so for those of you who saw my ITC colloquium, this is a bit of a different tack, but not unrelated. So I was talking there about the power spectrum of fluctuations in the early universe, and we're probing that with the 21 centimeter spin flip transition, which is usually at 1.4 gigahertz, but at redshifts of 10 and even higher, it's down in the hundreds of megahertz to tens of megahertz. And we can measure that. We would like to measure the power spectrum of fluctuations with experiments like PAPER and HERA. But there's a very important signal that is just the analog of the cosmic microwave background monopole, the 2.7 Kelvin, for 21 centimeter. And so this is just the spin temperature of all the hydrogen in the intergalactic medium as it progresses through the dark ages, where it starts tracking the kinetic temperature of the gas as it's cooling. It decouples because collisions get weak. It recouples once we have the Waldhausen field effect. Heating drives that spin temperature up above the CMB temperature, and then it gets ionized away and disappears. And this comes from the model from Jonathan Pritchard and Avi that they did here. And this signature is an important other piece of our understanding of the 21 centimeter signal at high redshift. We can trace it up to higher redshifts, and it also removes some of the model dependence of what we know about reionization. So this is a very important signal that we'd like to access. And people have been working on it a long time. It's a very fraught field with a lot of technical calibration demands that are quite difficult to meet. It would be nice to be able to use an interferometer to do that, because we know how to calibrate interferometers very well. But you say things like measuring 21 centimeter monopole with an interferometer, and that's almost a contradiction of terms. You have a monopole, which is a homogeneous signal across the sky, and interferometer differences two different measurements. So how could you possibly measure a monopole with an interferometer? I should say that all of this, I'm advertising work by an excellent undergraduate who just started as a grad student at Berkeley, Morgan Presley. She came out in a summer and did this work. It's absolutely fantastic. So as I said, we begin with the notion that you take a sine wave, which is what an interferometer fringe pattern looks like on the sky, and you average that, and of course it comes out to be zero. So how could you possibly lay over a constant signal on the sky and get something that overlaps? And what you have to invoke is that the sine wave only cancels out perfectly if you integrate over a full period of that sine wave. If you integrate over a portion of the period of that sine wave, or even if you integrate over multiple periods but end on a fractional period, there will be a residual bias that you end up with. And in fact, the sky is curved. It's not an infinite flat sheet, although people at higher frequencies will be forgiven in radio for believing that the sky is flat. It's actually curved and has a finite extent. And so if you project your fringe pattern from two telescopes up on the sky and integrate over the sky as visible, even taking into account that fact that you have primary beams of your telescopes that are starting to attenuate that, just the fact that the sky is curved and ends at the horizon sets a fundamental limit on what you're integrating over. And what this means is that even if you don't put your antennas physically on top of each other, even if they're close to one another, they can still have an overlapping region where they actually are sensitive to the monopole, that they measure the same electric field in phase with one another. And that's a somewhat counterintuitive and surprising result, which is why I wanted to advertise it here. And so another way of thinking of this for people who do radio interferometry is when you cross-correlate two different antennas, you're measuring a Fourier mode of the sky. These Fourier modes, which we label U and V, are Fourier transforms of the angular sky. And what this means is that you are centered at a Fourier mode that is not 0 when you cross-correlate two antennas that are next to each other but not on top of each other. And at the 0, 0 point is actually where the monopole term lives. But if you're close enough, the point spread function of your interferometer in this Fourier domain crosses over that origin, and so that's where you get your finite response to the monopole with an interferometer. So we've worked through the various details of a kind of simulation of an array where we take into account realistic effects. We model it off of the paper array that we know and love, and what we can do is parameterize the spin temperature of and its evolution versus redshift with different models. Like here, for example, the reionization cutoff we model as a tangent. We didn't invent this, but you can parameterize the different shapes that you see here and then ask what are the different kinds of constraints that we can get on these parameters, both with a kind of standard monopole experiment, which is usually just one dish, which are in the white contours that aren't black, and then what we could do with an interferometer where we have, which are the blue contours, 1 and 2 sigma in these domains. And what you can see isn't that there is some miraculous improvement by using an interferometer, even though you can use a lot more different antennas to do your measurement. There isn't this miraculous improvement in the constraints that you can yield. But it does show that, in principle, you can do this with an interferometer with a modest-sized array. What we were using here is, I think it was like 16 elements. So this is something we can build correlators for doing this. An undergrad can do it in a summer, and it's not that hard. And the point of it, though, is we know how to calibrate interferometers. We can also put in other antennas that are farther out and use a lot more of the standard calibration that we know to do with self-calibration for interferometers, and then apply that to this measurement here, and it still yields kind of comparable results to doing just this experiment with just a single antenna. So this is, we're proposing this as an alternative way for people to think about making this measurements if your systematics are getting too difficult for you with a single element. We can parameterize a different part of the absorption dip that happens when Waldhausen field effect kicks on when you have the first Lyman alpha photons coming out, and parameterize this as a Gaussian. And in this case, because you get a little sensitivity starved at lower frequencies, having more and more antennas that you can group together to do this constraint ends up you can make better constraints than a single element would in this case. But you could reasonably argue that I'll just put out more single element monopole experiments and make up that sensitivity. And that's a totally valid thing here. Again, the takeaway point is that it's in principle possible to do this with an interferometer, and it achieves results that are on par with anything you could do with a monopole. So in my remaining time, I just kind of wanted to walk you through a little bit of the intuition that if you grant me that an interferometer can measure a monopole signal, which some people just get stopped there, but if you grant me that, how would you design an experiment that would do that? Here's an interesting case of I've shown up here plotted is the primary beam response of a paper antenna. We have good models for that, and so I default to that quite often. And I can see when I Fourier transform that from the sky to what it does in the Fourier domain, you can see what that PSF looks like. So you can imagine if I shift that off to being centered at different U's and V's, how it would overlap at the origin. But say, for example, you took your antennas and you put them at the bottom of a very steep valley, just kind of throwing that out there, then, if the walls of this valley were absorptive, you would lose your primary beam response in those directions, and you'd only have it projecting up to the sky where it actually made it out of the valley. And in that case, the effective point spread function in this Fourier domain of your antenna element is actually much more distended in the UV plane. And you can imagine now being able to separate your antennas by a lot more, like you can read these as wavelengths, so by 5 or 10 wavelengths, and still have significant power thrown onto the origin. So this kind of opens up an interesting design space for how one designs an interferometer to measure a monopole. And I started researching where the steepest valleys are in the United States with the thought of perhaps putting some antennas in the bottom of that. Another thing I just kind of wanted to highlight is even if you take the primary beam out of this and just put your fringe pattern up on the sky, lay it over a full spherical volume, and do the spherical transform on that, get all your spherical harmonics as a function of L. It's a little hard to see, but you see that most of your response is at an L here that corresponds to the separation of your antennas. But it's by no means only at that L, and it rattles around, and there's a significant amount at L equals 0. Where's that L equals 0 response coming from? Well, it's actually the fact that next to the horizon, if you have two antennas and you look at them edge on, they don't look like they're separated by any distance. And that means that you're asymptotically approaching a zero separation interferometer, which is interesting. So this effect can be quite pronounced on even baselines of substantial length because our synchrotron sky has more and more power on shorter and shorter scales because it has a lot of diffuse emission. And in fact, the diffuse synchrotron can pile up at these areas where your baseline projection is getting shorter and shorter. And we see these in simulations, especially for dishes, this buildup of extra response by the horizon. And then what I've done here as my last plot is I took real paper data for a baseline and integrated it over several hours just straight. And what I did not do was phase the different parts of the sky. I just integrated it. So you'd think that everything that's moving around on the sky washes out, but a monopole, when you rotate it, still a monopole looks exactly the same. So a monopole would stay in phase as I did this. And then I Fourier transformed that. You can read the delay axis as essentially cosine of angle on the sky. And interestingly, there is excess power at 100 nanoseconds, which in this plot corresponds to the full length of our baseline, which means this was at the horizon. So an unsolved question that we're looking into is this a monopole of the sky? It may be sitting in our data already. I would emphasize that even though this is millikelvin of power, this has not compensated for the decreased response to the monopole. And so, when you compensate for that, this is almost certainly up in the hundreds to 1,000 Kelvin. This is not the monopole of reionization. This is the monopole of the synchrotron sky. But that would be a very interesting proof of concept if it's sitting in our data already. So that's it. So I think having an interferometer definitely helps there. I think another critical aspect of this, which actually Adrian Lewis, a Hubble fellow at Berkeley, pointed out in a very nice paper, is that spatial information is important, and having a larger dishes to kind of be able to selectively pick which part of the sky you're looking at is a critical part of this. But part of what we learned in all of this was that the foregrounds are still very, very, very much brighter than the signal. And even the added suppression we got from adding lots of different antennas around and being able to essentially project out other spherical harmonics that are not the monopole only bought us about a factor of 2 improved suppression in the angular domain, in the image domain of foregrounds with respect to what could be achieved with monopoles. And part of with single elements. So I was a little surprised that it wasn't a bigger effect than that. But it seemed like the spectral axis was more important than the spatial axis. And one of the costs of doing all the projecting out your different other spherical harmonics, so you only get the monopole, was it was very easy to introduce a chromaticism that would compromise some of the smoothness of response. So if one goes down that route, one has to be very careful.
Yeah, I was going to say that you're going to get the filling in along at high elevation along one axis. You still have the grating effect on the other axis, don't you?
Yes.
So I'm surprised that a 1D grating or a 2D grating, I would imagine it have similar effect in terms of the impact on your signal. I'm surprised it comes out so well.
Yeah. Well, so that grating was just a thought experiment. That's not actually how we've laid it out. But part of it was to illustrate there are two different effects. One is this horizon brightening from the projection of our baseline, and the other was the limiting your field of view. There's another interesting route to doing the changing your field of view that's been done with LOFAR by Harish Vedantam, which was to actually use the moon, which is moving around on the sky, as a mask, so that you make a measurement with the moon there, measurement with the moon not there, difference those measurements, and you've isolated the sky at the moon. And that's essentially like putting your element in a very deep valley with only a very small area. And that makes an interferometer capable of measuring the monopole again.
I'm just wondering about the peak at plus 100. Is that the other horizon?
Well, so this is a Fourier transform of the frequency domain. So interferometers generally have a complex response with a phase, but the monopole is unique for having for being a real valued signal on the sky. And that means that when I take the Fourier transform, it should be symmetric in positive and negative. So my first surprise in doing this was that this is not symmetric. I don't know the answer to why it's not symmetric yet. If I had seen a symmetric signal, I might have more strongly voiced what I was just saying about this being a monopole. I don't know if this is the monopole. It has a lot of the characteristics you'd expect a monopole to have, including the fact that it's at both plus and minus. Yes, there is. I'll get back to you on that one.
So you had this thought experiment about putting your experiment in a valley.
Mm-hmm.
But instead of that, could you put it in a cylinder, something like the UT or the Molonglo? Like, imagine the dipoles on a cylinder telescope. It looks only at a slice of the sky, right?
Yeah, unfortunately, the way it does that is by reflecting response that was heading somewhere else up onto that patch. And that's not the same thing as removing the response there. That if you take an isotropic response pattern of your dipole where it's doing some interferencing and then reflecting that up within a certain field, you'll still have all the pluses and minuses within that field, and they'll cancel out. What you need is to have, if you're going to do that, you need a giant cylinder of absorption. Yeah, the absorption aspect of this is fundamental. You have to remove your response there, not just reflect it.
But a reflector does remove the sky, right? A reflector of finite size. When you have a detector looking down at a reflector, the edges of the reflector are anything outside the edge of the reflector is shadowed out. Right? Reflectors have finite sizes, so outside of it is a shadow.
That's true. So if you're projecting it onto the ground outside of that, then that does help. And in fact, more on the kind of theory of how one would design this, what we're currently thinking is perhaps putting very planar elements on absorber directly. So they have forward and backward lobes of response, and we're purposely shunting the backward response of that into an absorber. It's an interesting idea.
This makes sense if the systematics on single dish experiments are up against the wall.
Mm-hmm.
I've heard that edges, which is one of these experiments, is doing pretty well. Can you comment on how well they're doing and if there's really an impetus for this?
Yeah, so I've seen some preliminary responses with edges. And so where edges is right now, if I can just jump over to here. So they're constraining, they have a high frequency version. Edges is run by Judd Bowman out of ASU. They have a high frequency version that is focusing on the reionization transition into not having any signal at all. And they have, I have to give them credit. They've done an incredible job trying to calibrate their system with on and off loads, and very carefully manufacturing everything to control for this. And what they end up doing, though, is they still have to get their synchrotron sky out as it is multiplied by all their instrument response, and they fit some order of polynomial to that to try to remove it. And the higher order polynomial you use, the more of the signal you lose. And so where they are right now is they can constrain and I think this is a forthcoming publication I've just informally seen for about 5 seconds a figure, so I shouldn't be taken. Okay, and I forget what the delta redshift that they're constraining is. I think it's of order half-ish, which is very interesting and starts to couple with the kinetic Sunyaev-Zildovich constraints. Interestingly, but if you ask, can you go further than that? I think that's where, in my mind, Edges has done the single element about as well as it can be done. Can we do better than that? Well, here's at least an idea to explore. I can't promise it does better, but it's an idea.
Thank you so much.
Thank you.
Oops, sorry. 1 second. A little bit of snafu. There we go. There. Hello, everyone. It is a pleasure to be here. I've just begun at Harvard University after teaching at Penn for several years in both history and sociology of science and in bioengineering. And my specialty is American human spaceflight, which I've studied for many years, and I have a lot of institutions to thank for supporting my research, including NASA and the Smithsonian Institution's National Air and Space Museum. I was a Guggenheim Fellow at Air and Space and currently serve as a research associate, working on several projects there. I go to the Air and Space Museum quite a bit, and because I often walk around with my badge, I get asked a lot of questions. And the question that I get asked most of all is actually, where are the bathrooms, which I'm more than happy to oblige. You'd think I'd get a lot of questions about, can I become an astronaut, or how can I become an astronaut, but actually relatively few people ask that. They assume that you have to be a military test pilot or be some kind of super scientist, like Professor John Frink, who Simpsons watchers will know holds an advanced degree in hyperbolic topology. If you are interested in becoming an astronaut, here's the address. Feel free to write them a letter. They actually do not like unsolicited application material at the Johnson Space Center. In fact, what they will do instead is direct you to, and yes, you saw it already, USA Jobs, where astronaut openings are actually listed with a rather short window to apply. And most of the initial stages happen through this internet portal. The space program still recruits basically two kinds of individuals, military test pilots, as well as scientists. And a lot of people don't realize, actually, that NASA offers wonderful opportunities for scientists, both on the ground and in space, and that their qualifications to become a scientist astronaut, effectively, or a mission specialist, are a lot less stringent than people might think. It is far easier, actually, to become an astronaut than, let's say, President of the United States or an A-list movie star. It's actually a reasonable goal for you to have. If you're not military test pilots, you'd be surprised at how little education and training you need in order to ostensibly qualify as a scientist astronaut. You will need a bachelor's degree in engineering, biological science, physical science, or mathematics, followed by 3 years of experience or 1,000 hours flying a jet airplane. Here's the really fun and interesting part. That 3 years of experience can be made up entirely by a doctoral degree in your chosen field. So literally, all of the ABDs and newly minted PhDs out there, congratulations. If you want, you could be astronauts. I should say, however, that the competition for these spots is extremely brutal. But NASA is quite serious about making sure that the people we send into space are capable of deriving some value from that experience. As you know, the National Aeronautics and Space Administration was chartered in 1958 as an institution to acquire knowledge and disseminate it to the world. And it's very serious about doing that now. In the early days of the space race of the 1960s, though, NASA's relationship with the scientific community, as many of you know, was somewhat fraught. In part because what motivated the space race was not a pure desire for knowledge, but a superpower competition. And although NASA knew that eventually it needed to launch astronauts into space who had scientific training, at least at the beginning it was far more concerned with making sure that it beat the Soviet Union to the moon. And this might require, as far as NASA's leadership was concerned, flying not scientists, but people who already had experience working with dangerous flying machines. Here we see the original 7 astronauts, the first American astronauts of Project Mercury, who were selected in 1959. They were all military test pilots who had significant engineering training. And their principal concern was not that enough good science would be done in space, but that NASA's engineers might decide that actually it didn't even need them at all. That the best way to explore space would be with a robotic spacecraft, or with a spacecraft that was remotely piloted and controlled and could be flown tolerably well by a monkey. Indeed, as several early space vehicles actually were. This is, of course, 1957's Curious George gets a medal. The earliest American space vehicles, and Soviet space vehicles for that matter, could be controlled from the ground. The interest of pilots was to make sure that future American spacecraft were so difficult to fly that nobody but trained aviators would ever be allowed to fly them. They had a significant role in the design of the spacecraft, particularly the Apollo spacecraft that would take American astronauts to the moon. And they made sure that the 500 or so switches found in the cockpit would require tremendous skill and training, that the space vehicles had the kinds of joysticks that were familiar to combat aviators and test pilots, and that no one would be allowed in the spacecraft who wasn't a trained and qualified jet pilot. But if the ostensible reason for going to the moon, at least publicly, was to generate knowledge and to perform science, NASA could not very easily hold off complaints and criticism from within the institution itself, particularly from Howard Newell, that NASA had to add scientists to its roster of military pilot astronauts. And grudgingly, those in charge of the human spaceflight program accepted, selecting the first group of scientist astronauts in the NASA program in 1965. Because everyone aboard an American spacecraft had to be called a pilot, it was decided at first that these men would be known as science pilots, because they would literally be flying their own experiments into space. NASA also wanted to make sure that they had at least basic competency in test piloting, so insisted that if the scientists did not already possess the ability and the rating to fly in high-performance military jet airplanes, that they get that training while astronauts. What we had, in fact, of the first selection of astronauts are individuals who actually could have come very close to being pilot astronauts themselves. Most of the men came to NASA already having a pilot's license or even some jet piloting training. Only the geologist Harrison Schmitt in the center had no flying training whatsoever. And as far as NASA's leadership was concerned, these men were not going to be astronauts or even called astronauts until they developed the proficiencies that pilots possessed, even at the expense of their scientific work. The head of NASA's astronaut office, astronaut Deke Slayton, insisted that people weren't even astronauts until they had passed flight training, that the critical skill, the important skill for flying in space was going to be piloting. He even resisted flying a scientist, a geologist, even on a lunar landing. It was obvious that a trained scientist on the moon would be very useful in terms of finding interesting specimens to examine and directing scientific research. As far as Slayton was concerned, himself an elite test pilot, scientists were a liability who would probably destroy the spacecraft if they tried to land it themselves. And as Slayton famously said, a dead geologist is of no use to anyone. In fact, there was an attitude in the space program that individuals like these scientists, astronauts, even though they themselves were actually quite capable engineers and scientists as well, were somewhat akin to the nutty professor. In fact, they were referred to as milquetoast academic types who had no military or piloting experience. A subsequent group of scientist astronauts selected by NASA in 1967 received a very poor welcome. On the day they showed up for work, Deke Slayton gathered them together into a hotel room and told them that none of them would ever fly in space because the space program was already winding down. There wasn't seats for them, and he saw no need for the scientist astronauts. In fact, NASA came very close to firing all of these folks after Apollo. Instead, they stayed with the program. And they endured the indignity of the fact that at NASA, everything was rooted around the piloting and piloting culture. Astronaut meetings were referred to as pilot meetings, and people spoke openly in derogatory fashion about scientists who had spent their lives in school and had never experienced the real world. Ultimately, though, due to pressure from the scientific community, one of the earliest scientist astronauts was sent to the moon on the final American lunar landing of the 1972's Apollo 17. Here we see Harrison Schmitt on the surface of the moon in his lunar module, having completed a spacewalk literally on the surface of the moon. Apollo 17 remained on the moon for 3 days. The astronauts were able to explore a great deal of lunar territory, particularly using the lunar roving vehicle that they were able to ride. Several other scientist astronauts were able to fly aboard the Skylab space mission, but others of the group, both in 1965 and 1967, left before they ever flew, including astronomer Brian O'Leary, who wrote a tell-all book about his experience called The Making of an Ex-Astronaut. He left the astronaut program during flight training because he actually found it very, very dangerous. In fact, many astronauts have been killed just flying jet airplanes. And he didn't see what connection there was to the actual work of being a scientist in space. He unfortunately said that he didn't think that flying was his cup of tea, which Deke Slayton found sort of emblematic of the lack of seriousness of American astronauts and reported to the press. Why didn't O'Leary leave? Because every time the scientists, astronauts became depressed about their lot in NASA, NASA took them to a launch. And when you see that rocket lifting off into the sky, if you've never done so, you will succumb to an illness called launchitis. A temporary insanity that makes you a space enthusiast, even if you don't really know why we're doing it at all. Thank you very much. The good news is that the next call for astronauts is actually going to open on usajobs.gov on December 14th. It will require the submission of a variety of materials. And at that point, there will be a cut for qualified and very highly qualified applicants, a series of interviewees followed by finals. But the good news is if you make it to the final cut, everybody gets a ride in a T-38 jet airplane. And a lot of the early astronauts of 1967, the scientists, signed up just for the free airplane ride.
So that's a wonderful picture of Kurt, of the 6 astronauts.
Yes.
On the left-hand side was Kurt Michael.
Yes.
He was Richard Feynman's last PhD student.
Mm-hmm.
He was my colleague in Texas.
Really? Wonderful.
We worked together for 5 years. Amazing thing about him was he was one of 10 Navy test pilots landing on aircraft carriers. Mm-hmm. And if you remember the Tom Hanks movie where the lights go out and they see the bioluminescent wave, that was him. That's how he found his way onto the aircraft. That's a true story. He's an amazing guy. He was one of 2 surviving of 10 test pilots on that one. What you call group regiment.
A remarkable individual who left the space program, and the headline was, he left NASA to pursue science. He was frustrated by the lack of the ability to practice his craft.
Well, he told me it was because geologists were getting picked over physicists. That's what he told me.
In fact, that was a significant issue.
Because the guy picking them had an earth science background.
Exactly.
I would argue that observers would be more likely
And then in Skylab, everyone had to be a solar physicist because that was the only way you could get flown. But
you just died 3 months ago. It's very, very sad.
thank you very much for sharing that. That's wonderful. Yes, of course. Microphone.
Shall I start? Okay, so I'm Alicia Soderberg. I'm a professor here, and my laptop just died. There we go. Hold on. There we go. And I wanted to highlight some of the recent work that we've been doing on supernova forensics as part of a large group of people, that many of which have spent time here and have moved on to other very prosperous endeavors. And in particular, this is a paper that focuses on 35 years of observations with the Very Large Array on Type 1a supernovae, which are, of course, famous for their use in cosmology. And this is the press release that came out this week. What's important to note is that all of these observations were done within 1 year of the explosion of the supernova. So they're all young Type 1a supernovae. These are not remnants. And so you might ask the question, what took us so long? Why did it take us 35 years to put together this whole compilation? And I could tell you that it's because the dog ate the homework. And that actually is homework. But that's not the case. That's my dog. She does eat homework. But actually, it's to pay tribute to Harvard, CFA, and Avi and the ITC for putting together this great group of what I would call young, if we still count as young, people that have helped make this possible. So everyone here has either been at the CFA or still is at the CFA, and we put this paper together. So what is the story? The story is that we found more than 6,000 supernovae to date. And these are just postage stamps. Each of them is a galaxy with a little blue dot. That's a Type 1a supernova. This was taken from Sloan. But ironically, only 85 objects have been studied in the radio to date. So this paper is the most comprehensive radio study of supernovae, young supernovae, within 1 year of explosion ever. And it has really benefited by the improved sensitivity of the Jansky Very Large Array, which is a factor of 10 better than the old VLA. And so you might ask the question, why do we care? I mean, we already won like the Nobel Prize, and certainly people here were involved in that. But we want to understand the physics still and the progenitors. So we want to ask the question, why can we not figure out if it's a single versus a double degenerate white dwarf system? And we have shown we can do this by diagnosing the environment around the explosion, whether it's a wind environment, which could be an indication of a single degenerate, red giant that is putting stuff onto the white dwarf, or it could be an ISM, a constant density environment, where you have two white dwarfs that in spiral. So we also want to understand shock physics, which is fun, feedback, just understand white dwarfs in general, dust formation, destruction, binary evolution, and maybe supernova homogeneity is something we might glean out of this study. This is also a great time to do it because there's these new optical time domain studies, such as pan-stars. There's improvements in our amateur facilities, and our communication with the amateurs has gotten so much better. And as I said, the improved radio facilities such as JVLA have helped us. And I think one of the neat things is it's provided a connection between nova, supernova, and the supernova remnant communities, so we can really get to the bottom of this. So what does a supernova look like? We all know what they look like. Here's a typical galaxy. This is supernova 98BU. This was taken by Peter Chalice, who's also right here. And they look like a pimple. If you look at the cartoon version of the frequency versus flux, there's a non-thermal signal, which is the straight line, and then there's a big optical thermal signal that is the pimple, and that's how we find supernovae. It's about 10 to the 42 erg per second. It lasts for a few months, and it's just a fortuitous coincidence that the nickel 56 decay timescale is similar to the diffusion timescale of photons through the ejecta, which is why optical is the ideal place to find a supernova. What we also do is try to pull in the other frequencies and understand the shock physics by using the X-ray and the radio and the millimeter when we have the opportunity. So it's always important to remember that supernovae are homologous explosions, and that basically means it's a Hubble flow of material that's coming out from the inside of the explosion. So there's a lot of stuff that's traveling very slowly at about 10,000 kilometers per second. There's a double shock system. The forward shock is interacting with material in the environment. Electrons get all excited and accelerated to relativistic velocities, and they produce radio and X-ray emission. So if you want to think about it in the terms of like an emergency room, if you want to study the photosphere right here, that's kind of like being the dermatologist. And we're out here trying to study the other part. And if you want to study the inside, that's kind of like the cardiologist. And we try to do all facets of that. This paper focuses on the synchrotron emission. The energy that's coupled to this material and the homologous explosion, energy goes like velocity to the -5th power. In the case of a type 1a supernova. All right, so how do we do this? We have a healthy type 1a supernova. It's found optically. Again, it's a pimple. And the supernova discoveries are found by both amateurs and also robotic searches. They're announced through the IAUC. And we pursue about 10 type 1a supernovae per year of all types. And I'll explain types in a second. And then we cherry pick like a few of them to go after for a long-term multi-wavelength study. And when I say types, it's because we always think of standard type 1a supernovae, right? I mean, that's how we do cosmology with them. But at the end of the day, we've learned that there's all different classes. So we define them in this paper, and also in a related paper by our postdoc, Jared Parent, who is also in the ITC. There's 1AX, there's low luminosity type 1As, there's calcium-rich events, there's cool, faint events, broad-lined events, shallow silicon events, super Chandrasekhar events, and then ones that are interacting with some sort of dense medium that's very far away from the star. So they're not actually homogeneous as well as we thought they were. And this is just the outline in our paper to explain all the different facets of this. And the result is, it's sort of depressing, but not really. The result is there's no radio detections for all 85 of these objects. And these are the models. This is a time-set explosion, and this is like 5 gigahertz luminosity here. This is what a synchrotron emitting source would look like. This is modeled after the models we put together for type 1bc supernovae, core collapse supernovae. So this is a wind environment here, and this is a constant density environment here. And these are all of our limits for type 1a supernovae within about 100 megaparsec. And we're assuming things about shock physics, like that that they are an equipartition, the amount of energy that goes into magnetic fields and accelerated electrons is equal, about 0.1. So we have a single degenerate scenario, we have a double degenerate scenario, and it looks like we're getting very close to ruling out the single degenerates. So what this paper demonstrates is that if you can take any frequency you want, and I only mention this in the sense that there is absorption, self-absorption in these bands. So going from 1 gigahertz all the way to 22 gigahertz, we show that all the limits are really ruling out the high density scenarios that you might associate with a red giant donor star for the white dwarf. And you can play the same game with a wind scenario, and here you can see that it's harder to rule it out here. And we've done more work in comparing this with what we know about the environments of novae, for example. So, I know you guys all want to go soon, so I just want to say, like, our final conclusion is that white dwarfs, however they produce type 1a supernovae, they eat clean. We basically say that less than 10% of type 1a supernovae are single degenerate red giant systems. The best limit we put on an object to date is a mass loss of about 5 times 10 to the minus 9 solar masses per year. That's for a wind velocity from the white dwarf of about like 10 kilometers per second. And so that's the record holder. And I just also wanted to advertise work that we are doing also. So this is a indication of that radio might actually serve as a tool in which we could decipher type 1 BC supernovae from type 1, because 100% of type 1 BC supernovae are detected in the radio within 10 megaparsec. And so this could be used, whereas 0 are detected for type 1a. This could serve as a diagnostic in addition to optical information. And we also study the older objects. So this is nice work done by Sion. This is the youngest type 1a remnant in the galaxy. So make new friends, but keep the old ones. You have to study all of them, the middle-aged ones, the young ones, and everything. And maybe we'll get to the end of it. So, yay, that was perfect.
Alicia, is there uncertainty in the model parameters for the Soderberg prediction? Because even if you have a shock, there is how much energy density there is behind it, what's the fraction of post-shock energy going to relativistic electrons and so forth. Is that any issue in terms of?
So in the paper, we go through all of that. So we keep the 2 epsilons constant. We assume equipartition for most of it. But then we do allow the magnetic field to be lower. That's one thing we do. And we do assume that the reverse shock and the forward shock have the same equipartition parameters. We don't let them vary as a function of time. We keep them steady. So all of that should be done in more detail, but I just think it's an interesting diagnostic that we see radio emission from type 1 BC supernovae, which are also hydrogen-free, and we don't see it from type 1As. So it actually confirms the fact that we know what we're doing when we look at optical spectra. We are classifying them correctly, I think. Oh, hi.
You give a prediction for the radio emission based on the progenitor of double and single degenerate, and also consider the environment about the wind and the interstellar medium. You showed a picture about the light curve or the spectrum there, but I wonder you could, yes, the up is for the wind.
This is wind, yes. So this is the synchrotron self-absorption that is pulling in here, because it takes longer to sweep up material depending on which environment you're in. Constant density media, as shown by Sion's paper, take longer, rise faster. These guys fall.
But for the single and the single degenerate and the double degenerate is from the progenitor, and the wind and the interstellar medium is for the environment. Why you use this? For first of all, if we consider the single degenerate, that for this degenerate, we have considered the wind and the interstellar medium for the 2 kinds of environment.
Okay, so you're basically saying, do you have a constant density medium around your white dwarf? Is that what you're asking?
He's asking why is the single degenerate associated with the wind while the double degenerate associated with the sun? Is that the question? And the point is that in the single degenerate, you have another star that is producing the wind. The star next to the single degenerate, there is a star donating mass that eventually leads to accretion and the supernova explosion, right? So the same star that is next to the white dwarf is producing a wind, and that's what is the origin of this expected radio emission.
It's sort of like this. Yes, I'm sorry. It's sort of this scenario. So you have this wind that's being blown onto the white dwarf, and so then you would expect to see junk in the environment. Whereas it's just 2 white dwarfs spiraling in and smashing, then there'll be nothing. Yeah, I'm sorry. I should have said that. Thank you. Thank you.
Yeah, give me an email. I'll bounce one back.
Perfect.
Huh?
Looking forward to your
Oh,
talk.
good. It'll be fun. It'll be fun. Bring a tomato. You can throw it.
I'll do that. I have a little bit of a sandwich.
Great, chuck that. You chuck it that way. I hope you end up eating.
What is this? What is this that was talk? I forget.
Very nice talk.
Oh, thank you.
Very clear.
I don't know. I don't know.
You still got the...
I sure do. I will get it. What's the title?
I did
of
that
this
once. I was like walking away.
What is he talking about? Oh, you're his host.
No, I'm not his host.
Oh,
yeah.
do you know what he's
Gonna
talking
go.
about?
I'm not sure. I mean, Dwarf Galaxies in some context, but I don't know. I don't remember the title.
Gotcha.
Sandwich.
Thank you.
Thanks.